Thank you very much. Actually, I would like to call my second name Hamid, but here is written Seyed anyway. Okay, the structure of residual intersection. This is the main result here are joint work with Vinicius Busa, the guy here. Okay, so if you ask me to choose, maybe to describe or to choose one of the word important, central, or natural for residual intersection, I mean to explain residual intersection better, I would choose natural. So for that, the reasoning is that residual intersections are natural objects that may appear naturally everywhere, and soon I will give you some examples. But if you say, oh, so why didn't you say important or central? And I will say important and central are something that people are interested in and lots of people are working on. And although residual intersection is a beautiful theory, but there are something that prevent people going there and working like vigorously on the topic. And this is due of several aspects of the topic, and some of them are complexity of the theorem that you encounter in that theory and difficulty of the result. Although at the end the results are very surprising and interesting, but the way that you go there is very difficult. And my idea is that this topic deserve actually due to its naturality to be developed much more than this. So let me explain to you some little history. So if you want to track back the history of residual intersection, I learned this from David Eisenbach, that residual intersection goes back to the middle of 19th century, so 18 something, and maybe to Schaas, if I pronounce correctly the name. So Charles, okay, Charles. And so when he described, so he actually counted that there exists exactly 3264 conics tangent to 5 general conics. And it was interesting at the time very much, but this is the way that actually lead you to the enumerative geometry and intersection theory and whatsoever. Conics that are in the plane. Tangent to 5 general conics in general position. Maybe this is not the general position. Anyway. Oh, this is 6. Okay, sorry. Anyway, this is neither in the general position. Okay. But anyway, the situation is more natural than this. So whenever you are working with a variety in Pn given by at most n+1 equation, and you take out some part of this, right, so that the remaining part are some points, then you are working with residual intersection. Okay? An instance of this is the theorem of Cayley and Baccarat. Again in 19th century, so they showed that if you have 2 cubics in the plane, so like this and this, so they intersect in 9 points, and then if you have a curve passing through 8 points of these 9 points, so the curve must pass through the last one too. Okay, so this is the same idea. So you have a variety, you took out some part of that, and what remains is only 1 point. So this is the very first example in the real, I mean the modern residual intersection. And this example also connected to the Pascal theorem. And maybe it also goes to the old what's the name? The theorem of Pappus theorem. And if I go back, if I go, I don't want to go back. So you know, Pascal's in the 17th century. So if I go back, I will get to Adam and Eve. I'll say you that they were working on residual intersection, although they were not aware of that. Okay. Anyway, in the modern language, it was the first time Artin and Nagata in 1972 who introduced the concept of residual intersection to the community of commutative algebra. So let R and M be a Cohen-Macaulay ring. Then we say that J is an S residual intersection of I if there is S elements in I such that J is a column I or R, and this A is the ideal generated by AIs, such that height of J, codimension or height, is bigger than S, and it is not dangerous to assume that S is at least G. I mean, the interesting cases are when S is at least G. So okay, let me explain a little bit the definition. So residual intersection, as you would expect, is residual. So residual in geometry correspond to the column ideal in algebra. But here, you ask the height of the residual to be at least number of equation of the original variety, right? Okay, this is what residual intersection defined. And you see just at the beginning that, hello? Okay. So just at the beginning, the Cohen-Macaulay hypothesis appear here. So one may wonder what such a basic thing needs Cohen-Macaulay. And so this is for two reasons. First is that, so maybe reasoning for that has two motivation. One, the questions come from, and second, where the properties are going to. So in this setting, Artin and Nagata were interested to prove that, to find the cases that R over J is Cohen-Macaulay. So because they were interested in these properties, so they assumed Cohen-Macaulayness at the beginning. Anyway. So we say that residual is geometric. So to the end of the talk, so G is the height of I, and S is number of generators of A. So the residual is geometric if, in addition, height of I plus J is at least S plus 1. So they don't share a primary component of height S. So the sum of I and J is at least S plus 1. I'm very happy talking among commutative algebras because I don't need to justify all of these definitions. So you are our friends. So I don't understand what I'm saying. In Brazil, it's very difficult to find community of commutative algebra. So you always talk to geometers, and you have to justify why this definition makes sense and so on. So, nothing. That's great. This is the importance of residual intersection. We don't want to assume anything except the number of the quantity of the generating set. It's just A, an ideal. Take out, you know, looking at geometric side, or here you have your ideal I, and you look at S elements in mind there. But then you wish the height of the column be bigger than this number. This is not trivial hypothesis. Okay. Okay. So the motivation of Artin Nagata was to study the the set of critical points from variety x to a variety y. So if you want to study the set of double points x1 and x2 that sends to a single point y here, then you will understand that this situation is connected to residual intersection, and this was their motivation to define residual intersection. Anyway, I don't want to go through this here. On the other hand, from another perspective, residual intersection has connection to the linkage theory. And it indeed started after the Second World War when the French Academy of Science proposed some question to classify the curves in P3. And it was Appert and Gata who defined the notion of linkage at that time. And then Peskin and Spiro in 1974 they define what we know nowadays as linkage. So they use R to be regular, but just Cohen-Macaulay will be enough, will be compatible with residual intersection. Let R be a Cohen-Macaulay. We say that I is linked to J via alpha, where alpha is a regular sequence if I is alpha column J and at the same time J is alpha column I. So here alpha is a regular sequence. But for residual intersection, we don't need that. So when these two coincide, so in very special case, so let's assume R Gornstein and I are mixed. So no embedded associated prime of different height or isolated prime. Then any G residual intersection is linkage. And vice versa, right? So this is the very special case of residual intersection. So in the Gornstein ring and for unmixed ideal, if you work with the extreme case, when S is exactly the minimum possible, then residual intersection and linkage is the same idea. But in general, even G residual intersection in the non-Gornstein case and non-unmixed ideal is a more general aspect than linkage, right? Anyway, so good. Is it clear, everything here? Okay. So the main theorem, linkage trivially applies residual intersection because in the Cohen-Macaulay case, when J is alpha column I, so the associated primes of J are among the associated primes of alpha. So when alpha is a regular sequence, so of length, so then here this says that I times J is in alpha. So the length of alpha is bigger than height of I and J. So then alpha is a regular sequence of height at least G. So J has associated prime among associated prime of alpha, so this has height at least G. So linkage is always residual intersection, at least in, I mean, we even don't need Cohen-Macaulay, maybe just Noetherian. Killer? G residual intersection of I. Yeah, correct. When J is linked to I, then J is a G residual intersection of I. And I is a G residual intersection of J as well. But this is not the case in the general. Okay. Okay. So the main theorem of maybe one of the important theorem in the paper of Peskin-Spiro is the following. So when R is Gornstein, I is linked to J via a regular sequence, then I Cohen-Macaulay, so R mod I Cohen-Macaulay, if and only if R mod J Cohen-Macaulay. This was one of the most important theorems of Skin and Spiro. But they themselves, Skin and Spiro, gave a counterexample where R is Cohen-Macaulay. So there is a counterexample where R Cohen-Macaulay, I linked to J, R mod I Cohen-Macaulay, but R mod J not Cohen-Macaulay. Interesting. You know, you need Gurnesteinness to prove something about Cohen-Macaullayness, but not Cohen-Macaullayness. So it is one of the first places that, you know, some extra hypothesis is needed, and maybe we don't have enough reasoning for that. Just a counterexample, right? So to improve this theorem, Honicke in 1883, so he introduced the concept of strongly Cohen-Macaulay ideas. So I thank Sean. He already introduced Koszul complex, and now I'm going to use it. So Honicke defined strongly Cohen-Macaulay ideals So we say that a module is, so we say that I is a strongly Cohen-Macaulay if all of the Koszul homology of a generating set of I, so I just write I here, are Cohen-Macaulay R module. Right? So there are Cohen-Macaulay R module of dimension D minus G, where D is dimension of R, and G is the height of I. So when all of these things are Cohen-Macaulay, so we say this is strongly Cohen-Macaulay. So there are non-trivial examples of strongly Cohen-Macaulay, like Lichy ideal, so linkage class of complete intersection. So if your ideal is linked to link to link, somebody that at the end is linked to a complete intersection, then it is strongly Cohen-Macaulay. Perfect ideals of height 2 are strongly Cohen-Macaulay. Perfect Gornstein ideals of height 3 are strongly Cohen-Macaulay. There are plenty of non-trivial examples of them. So the idea why Honicke defined this was that, so when you work with linkage, so you take out the maximum regular sequence of your ideal I out. So you are working, you know, your ideal is height I, height G, and you take out alpha 1, alpha G from I. So if you divide this with alpha 1, alpha G, this even, yeah. Yeah, then you actually figure out the top non-zero Koszul homology module of I, right? So the last non-zero Koszul homology module of I, so let's assume I is generated by R element. So all of the Koszul homology from R minus G up left are 0. And this is the last non-zero Koszul homology. And this is this. And this is indeed our linkage. So Honicke's intuition was that, so linkage is related to the last Koszul homology. So if I want to overcome this problem here, and I assume that all of the Koszul homologies are Cohen-Macaulay, then inductively I can get to the zeroth Koszul homology. And this is the way that he inductively could prove that if I is a strongly Cohen-Macaulay linked to J, then J is Cohen-Macaulay in a Cohen-Macaulay ring, right? So he proved that R Cohen-Macaulay, I is strongly Cohen-Macaulay, then J Cohen-Macaulay. Not bad. Good. And what if you want to go further? So remember that we are in the case of linkage here. So here S is G, right? And this is the theorem of Honicke. And if you want to go further, then you wish to prove something like this. Any S residual intersection Cohen-Macaulay. But this also was not possible at the time, so they had to add one extra condition called the GS condition. And this says that mu of IP is at most height of P for any P with height P less than S. So, you know, this is a kind of those conditions that when one looks at, so doesn't like the topic and maybe don't wish to continue because it's just not convenient. But anyway, so, but they proved that. So Hunike and Urish work a lot on this theory, and assuming GS conditions, so they proved this. Yes, here is strict, but here is equal. Yep. Correct. You know, yeah. Is it strong? No, actually, this condition was defined by Artin Nagata. And so there was a rank theorem in the famous paper of Artin Nagata. So the main theorem of the paper of Artin Nagata was wrong. So they wanted to prove that R Cohen-Macaulay and GS, then NES residual is Cohen-Macaulay. So this was wrong. It discovered by Hunike. But then Hunike added strongly Cohen-Macaulay and proved this. Right? So this GS was from the beginning. So one was from the definition that Artin Nagata gave. But then in 2012, I showed that indeed this is not needed. So forget GS. Okay, so if you are in the Cohen-Macaulay case and your ideal is strongly Cohen-Macaulay, then any ES residual intersection is Cohen-Macaulay. I also relaxed this condition a little bit. I don't want to go to the details, but it works like that. But what I want to talk today is a more general theory that we discovered with Vinicius. Not only Cohen-Macaullayness of residual intersection, but the structure of residual intersection, right? So you have your variety, you take out that variety, and you want to understand the residual. You want to understand the generators of the residual, right? At least the number of generators of the residual, or the Betty numbers, or some very basic question about residual, not only Cohen-Macaullayness. This ends the question about Cohen-Macaullayness, right? So now, I want to go through the structure of residual intersection, which I mean the generating set of J of the residual intersection. And so before that, so let me remind you some of the cases that were known before we work on this. So what about, so the question is, what are the generators of J? So this is a very basic elementary question. So known cases, you will see, are very special. So the first one was discovered by Piskin and Spiro. Of course, in the case S is G, and I is perfect, Cohen-Macaulay. Perfect and Cohen-Macaulay, right? So in the case of linkage, they could explain what are the structure of the ideal J, and also explain the resolution of J in some exact, maybe not minimal resolution, but resolution. But when you go higher from G, so then there is a result of Eisenbad, Hunike, and Urish. Chardin. Eisenbad, Chardin. So Chardin, Eisenbad, and Urish. So they show that when, of course, their proof is over polynomial, but I think it's worked over any Cohen-Macaulay ring. So they prove when I is a perfect ideal of height 2, so perfect height 2, then they show that J indeed is the fitting ideal with 0 of I mod A. Let me just show you how this proof works. And then the next step is, of course, perfect Gorenstein height 3. So then Ulrich and the Kostin, so they prove that in this case, number of generators of J is at most 2 to the S minus 1. Right? And then there is the complete intersection case. So I, a complete intersection. So then there is a proof of Hunicke-Ulrich 88. And there is one by Bruns, Kostin, and Miller around the same time. So then they gave, so this Hunicke, so both of them using very strong techniques. So then they proved that, so let's assume your ideal I is given by F1, Fr, and your ideal A, which is A1, As, and contained in F1, Fr. So this A is given by a matrix, C11, C1R, CS1, CSR, times F1, Fr. The content of the ideal here. So then they prove that J is indeed IR of this content matrix plus A. So a very clear description of the generators of the residual intersection, right? So you have your ideal I, you have a sub-ideal, so this sub-ideal is determined by a matrix, and then you just look at the R by R minors here, and this plus A determines exactly this. They use a theorem of De Concini, very geometric things to just explain the generators. And here, well, here, this theorem, although it is very specific, but it follows from the Eisenbach and Buchsbaum criterion of the acyclicity, right? So you have very special ideal I generated by R element related in R minus 1 element, and then you have your ideal A here. And then if you look at the mapping cone of this matrix, of this, you will see that I mod A is presented by R element and related with R minus 1 plus S elements. And the difference here, plus 1, is exactly S, which is the codimension of J. And this is exactly what one needs to say that in the Buchsbaum criterion, the annihilator of the guy is exactly the fitting ideal. Okay. When? Which equality? This is equality. And this, I think when residual is geometric and ring is Gorenstein, then it is equality. You are right. You're right. Good. Yep. Sure. Good. Thank you. Okay. Okay. I would say, do you wonder if I say that these were all known cases during, until this year? General things, as one can say. SGI perfect. So not even any ideal, just in the case of linkage, you need perfect ideal. And then perfect height 2, perfect Gorenstein height 3, complete intersection. That's it. This is the whole list that we knew. So then we start working on this, and it seems a very difficult question, I would say. Very difficult question to explain the generator of a residual. Not an easy job. There were also some other partial thing, not clean like this, about number of generators, but also, I would say, if I want to really complete the list, so the next step is when S is G plus 1, I is Lichy, and I is Gorenstein, and generically complete intersection, then Ulrich and Costin and I think Miller, so they found a bound for J. I would say this is the complete list. No exaggeration here. Okay, so then we wanted to work on this. I hope I can finish this lecture at least. Okay. So the idea was that if linkage is related to the last homology, residual intersection must be related to all homologies and all cycles of the Kuzel complex. But here, we not only need to look at the Kuzel complex as a complex of modules, but we have to look at the Kuzel complex as a differential graded algebra. Okay? So let me set the notation. So I would like to work on a commutative Noetherian ring. I would say that what I'm going to say maybe is not needed Noetherian. We only need finitely oriented ideals. So let I be generated by F1, Fr, A generated by A1, As, and let's assume that A is a matrix here, C times F. So this C has some columns here. So C11, C1R, CS1, and CSR. Okay, and then I would like to look at the Kuzel complex of these elements in the ring R. Okay, but not just the Kuzel complex as a Kuzel of module, a complex of module, but the differential graded algebra defined by these forms. And then you look at the columns of this, the rows of this matrix in this algebra. So then look at the forms like Ci generated by the rows here. So like Ci1, E1, Cir, Er. In the first component of the Kuzel complex here, and then you look at the algebra. So gamma would be the algebra generated by Kc1 and Kcs in K. So K is an algebra, and you look at this element as an element in the algebra. You look at all of the multiplication and sum of them. So you have a sub-algebra of this algebra. And also you look at the cycle of the Kuzel complex as a sub-algebra of K. And then you look at the product of these sub-algebras. So this will be another sub-algebra of the Kuzel algebra. Any question? Oh, sorry, Z. The sub-algebra generated by all products here. So a very, And then this is living here. But then look at elements who are living in degree R. Degree R is the top element here. So K is a exterior of AR is living between 0 and R is R. I mean, the R's component is just R. So the R's element here is living in KR, which is indeed R. So this is an ideal, right? And we call this ideal the kit. This is the kitty. And the name comes from Kuzel and fitting. So K comes from Kuzel and it comes from fit. So it is a combination of Kuzel and fit, so it is kit. So we define the kit ideal here. And then the funny theorem, an important, I would say, theorem appear here. So it is with Vinicius. And we just accepted this in Commutative. So so I summarize the theorem here. So the first interesting fact is, like fitting ideal, this kit ideal does not depend on the generating set of I of A and the representative matrix that you would choose here. So it's independent. It's like KIT. So KIT AI only depends on A and I. Okay, the second thing is that the radical of KIT is just the radical of J. So set theoretically, this is the one that you need, and nothing here, your ring is just commutative, not even Noetherian. You don't need to assume J is a residual intersection. So J is just a column ideal here. J is a column I. So this is a very general thing. If you want to theoretically work with, residuals in this sense, not residual intersection. Okay, then you prove that, maybe I'm just out of time, but I will finish this theorem. KIT, although we derive this from cycles, but it only depends on the homologies. So it is A plus gamma times the representative of the homologies of H. So not on cycle, but homologies. So it makes it wonderful, because then you have lots of application out of this. And in the case that R is Cohen-Macaulay, J is an S residual intersection. S is at most G plus 1. Then KIT is J. Okay, this is already something. And if you assume R Cohen-Macaulay, J and S residual intersection, S anything, but you assume R is strongly Cohen-Macaulay, then KIT is J, and it is Cohen-Macaulay. Okay, so this recover all these two cases, these three joint, recover all of the known cases, like perfect height 2. So maybe how much time do I have? 1 minute or 2 minutes, or just 4 minutes? Ah, good. Okay. Okay. I'm now relaxed. Okay. Okay, so this is the main big theorem. The proof is complicated. I don't go through that. It's a combination of the, let's forget that. So then let me just explain how one can apply these to the previous known cases, right? So for example, you go for example, you go to the case of linkage. So when S is exactly G, right? So corollaries. So when S is G, J is Cohen-Macaulay if and only if the last cycle in the Kuzul complex has depths at least D minus G plus 1, if and only if. So this answer the question, and provide lots of more counterexample, as the one that Peskin and Spiro constructed. And you see in the Cohen-Macaulay case, the Cohen-Macaulayness of a linkage is governed by the depths of last cycle, not the last homology, which is the canonical model. In the case of complex intersection, for example, when your ideal is complex intersection, then there is no homology except the zeros 1, right? So Kuzul complex is cyclic, so you have just H0 here, and the representative of H0 is just 1, so you just look at the algebra generated by the matrix there, and it is just AR of phi, right? So then this algebra times 1 is just AR of C, and this recovers the theorem of Honecker-Risch. So in the case of, for example, perfect height 2, then there is a theorem of Avramov and Herzog saying that the cycle of Kuzul is generated by the first cycle. So if you put first cycle here, if you put first cycle here, so the algebra generated by first cycle and gamma is just a representative matrix of I over I, right? And a representative matrix of I over I is just fit 0 of fit 0 of I over A. So this recovered the theorem of Eisenbach, Chardin, and Urish. But the difference, the reasoning is completely independent. This comes from the, this theorem of Avramov-Herzog about the generators of Kuzel cycle as an algebra, not as a module or vector space. There's an algebra, and then it reflects to the fitting ideal of I mod A. And okay, I think I will stop here. Well, here, of course, there is something. Thank you for asking me. So if you want to drop this, here I don't say anything because at the end you want to prove something is Cohen-Macaulay. So you need some Cohen-Macaulay here. But here, to prove kit is J, you actually don't need Cohen-Macaulay. You can say R Noetherian. And instead of defining residual intersection like height of J bigger than S, you say that grade of J bigger than S. Then it works through. So you don't need Cohen-Macaulay for equality, indeed. So we conjecture that kit is always J when J is a residual intersection. So we prove this conjecture in this level, but we believe it works in general. But we have example that if you don't assume residual intersection, kit is not J. So a general column ideal is not just kit. There are examples. But if you are residual intersection, then kit is J. This is conjecture. Kit. J, I mean, like this, you need elimination. You have to add a T and then eliminate T to recover J. But here, to compute K, to compute kit, you have your Kuzel cycle, which is computationally easy, and just you multiply this to the generators of A. It is computationally less complicated than elimination theory there. Cycle of Kuzel. Kuzel of I. You have your ideal I. You have the cycle of Kuzel. It's not difficult because Kuzel matrices are all linear. So the main question left is proof kit is J. Proof kit is J. Then you can prove lots of theorem about Cohen-Macaulayness of residual intersection, something like this, if and only if.